Hello everyone, welcome to the first episode of GDSC experiments. In this series we'll be tackling cool simulations, algorithms and optimizations, mostly within Unity, and today we're starting with the flocking or Boids simulation. Boids are just objects which simulate the behavior of birds. The core of the model revolves around three simple rules: alignment, which makes them steer towards the average direction of their neighbors; cohesion, which draws them towards the center of the group; and separation, which ensures that Boids don't bump into each other. Now within Unity, let's start by declaring some settings for the Boids, and a Boid manager script which spawns and controls these Boids. I'll try to implement the alignment rule first. To calculate the alignment, we first get all nearby Boids within a certain radius. We'll take the average of their forward directions or forward velocities, and this is the direction that our Boid should be pointing towards. To smoothly transition between our current direction and the desired direction, we'll need to apply steering force to the Boid over some time. This force is simply the difference of the desired and current velocities, and when applied, smoothly aligns the Boid with the rest of the flock. Now inside of Unity, I've set up this function which takes a list of all the Boids and iterates through them. The isValidBoid function checks whether the other Boid is close enough to the Boid calling the function, and if so, we add up the velocities, take their average, and return the steering force. If there are no nearby Boids, we'll just return an empty vector. Let's see how the Boids are doing as we gradually increase the alignment radius. It looks like what we wanted to see, so let's move on to cohesion. This is probably the simplest rule. All we do is calculate the average position of nearby Boids, and this should be our desired direction. We can simply steer towards the direction and move to the average position. The code for this is almost the same as alignment, except we add the positions of the neighbors rather than their velocities. As we increase the cohesion radius, the Boids start to form small groups, and with a big enough radius, they all converge at one point. To calculate separation, we need to move away from nearby Boids. To do so, we'll take the distance vector to a neighbor, and we want to move in the opposite direction, so we'll flip that around. The separation vector can be found as the distance vector divided by its magnitude squared. Doing this for all the neighbors gives us these weighted vectors, and when averaged out, they tell the Boid where to move. And here's the code for that. With separation enabled, the Boid always tries to move away from each other and appear to jitter more or less in the same place. Let's put the three rules together, and I'll also color the Boids based on their speed to make things look more interesting. This looks pretty cool, but the movement isn't very natural, and that's because we're updating the Boids' positions sequentially one by one, when all of their positions should update at the same time after the calculations are done. We can fix this by simply recording the Boid state at every iteration and updating the actual position and velocity only after the calculations are over. Right now I'm rendering around 500 Boids, and this looks great, but we're only getting 60 frames per second and we can do a lot better. If you have been paying attention, you would have noticed that the three rules require almost the same kind of calculations, and so it would make a lot more sense for us to run them all in one loop. At 500 Boids, this increases the performance by over 130 frames, but let's see how it handles 2000 Boids. That's not so great. We could try to implement a smarter way to find nearby Boids, like Raycasting, which I'm already doing for the obstacle avoidance, but either way, our main bottleneck is actually the CPU. So the CPU has less number of cores and performs tasks one by one, whereas your GPU has a lot more cores and can do things in parallel. But it has an Ooga Booga caveman brain and cannot do anything without the CPU telling it what to do. In Unity, we can achieve this by using a compute shader. Using this, we can send data into the GPU, the shader will process the data, and we can get it back. When you first create a compute shader, you'll see something like this. The first line defines the entry point of the program as the CS_main function, and we can specify how many threads we want running this function. We can create some variables and also a buffer, which is like an array storing a data type, which can be a predefined data type or any other structure that you define. We'll usually be passing data around through these buffers. Now you can run calculations on these in parallel inside the CS_main function. Over on the CPU side, we'll define some references to our compute shader and kernel ID, and we'll also create a compute buffer which will offload to the GPU. We can find the kernel ID using the findKernel method and can set the values of variables using the setInt or setFloat methods. To upload the buffer, we'll create the same structure that we defined inside of the shader. We'll create a new buffer and give it the number of elements we want the buffer to hold and the size of each of those elements. Since the data struct has 2 floats, I've put in size of float times 2. I'll populate an array with the values we want to send, and we can set the compute buffer's data to this array and finally set the buffer. To run our shader, we call computeshader.dispatch with the kernel ID and the number of thread groups we want. And to retrieve data from any buffer, we call buffer.getData, and the argument is where we want to store that data. I uploaded the Boids data to a compute shader, which does all the calculations, and now for 2000 Boids, we have pretty good performance without having to implement any fancy logic. I encourage you to mess around with this and try to implement things like multiple flocks, extrapolating this to 3D, and also check out other optimizations such as spatial partitioning. That's all for today, and I'll see you in the next episode of GDSC Experiments.